Hi, in this video we are going to go over the solution to the cats in corners problem from the example final. So what this problem wants us to do is model if 4 cats started in corners, how they would move towards each other. So in this animation you're seeing on the screen is what we want our final plot to look like, where it's changing over time. So each time step the green square is moving towards the black dot, the blue triangle is moving towards the green square, and the red circle is moving towards that blue triangle. So how our code should start is by starting with the initial locations of each of our cats. So we can do that by, or one way to do that is by creating an array where in the first entry of the array I put the X location, and in the second entry of the array I put the Y location. So XY, XY, and XY. And then I've gone ahead and plotted the original positions by saying plot XY, and then here's my green square, my blue triangle, the red circle, and the black star. And I've also changed my line width so that I can see them a little bit better. I'll want to go ahead and make my plot look nice, and I can do that by changing the font size, making the axis equal, so this means 1 meter in the Y direction is equal to 1 meter in the X direction, setting my axis so that we only see that 10 by 10 room, adding an X label and a Y label, adding a pause. So pause will pause your code for a given amount of time. Here I put 0.2 in my code, and that will pause it for 0.2 seconds. This number we might have to change around a little bit if you find the video goes too fast for you to see anything, or if it just goes so slow. But that's something that we can change later on. So here I've just shown us a schematic of where our cats are at, say, any given time. This should be a star, just ignore the fact that it's a circle. But let's first talk about Fluffy. So each time step, Fluffy moves towards Garfield. But as the problem said, Garfield just stays in the corner eating his lasagna. So each time step, we should have F running towards G. So F of 2, the Y location of F, should change by -1 each time step. And the X location does not change because Garfield is always staying there, so F is always going to run towards G until we get to G, in which case we will stop. So let's program that. So to step through our time, we're going to have a for loop. So let's have for I equals 1 to 15. So here the F1 location we said is not going to change, so I could just say F1 equals F1 or not. And the F2 location is going to be F2 minus 1. So the Y location of Fluffy is going to change each time step by -1. And here we should have, or maybe we have an if statement that says if F2, if this is greater than 1, so sorry, greater than 0, so if we're not at the origin with Garfield, then we should do that. Else, don't do anything, so I guess we don't need an else statement, so let's do end. And then here we're going to plot again in our for loop. We don't want to create another figure, so we're not going to copy that figure, and then let's do end. So if I run this now, I should have my F location. So my green square should be moving. Let's try it out. So we see each time step, the green square was moving towards Garfield until we stopped. The next two, so our blue triangle and our red circle, are going to be a little bit more complicated. So let's look at those next. So now that we've got an F, or Fluffy, moving in the correct direction, let's look at S, or Schrodinger. So I've drawn the triangle here between F and S. So the change in X, the delta X, is F1 minus S1. So the difference between the X locations. Note, I put F before S because if F is to the left of S, that will give me a negative delta X, and I want S to run in the negative direction. Same with delta Y. So I have F2 minus S2. So right now F2 is smaller than S2, so I want S2 to decrease or go down in the Y direction. And here my H, or my hypotenuse, is the square root of dx squared plus dy squared. And then the way that we're going to program this is the X location of Schrodinger is going to be the previous X location of Schrodinger plus the change in X divided by H. And here I have a typo. This should be the change in Y divided by H. So it should be the Y location of Schrodinger is the original or the previous Y location of Schrodinger plus the change in Y, so that's a typo, divided by H. So let's program that. Looking back at my code, I want to calculate dx in H before I have moved Fluffy. So I want to calculate, all of my distances before I move any of the cats, because the cats are kind of moving synchronously. So it's not F chases G, then V chases S, then, and so on, or S chases F. Okay. So here we will have, first we're going to calculate distances between F and S. So here we have dx, and I'm just going to put it in the first element of dx is equal to F of 1, so the X location minus the X location of S. Dy of 1 is equal to the Y location minus the Y location of S. And then H is going to be the square root of dx squared plus dy squared. And then down here, I should have that my S of 1 is going to be S of 1 plus dx divided by H, and S of 2 is going to be S of 2 plus dx divided by H. But let's also account for if we run into our Garfield. So if we hit that corner or run into one of the other cats, we shouldn't continue going. So let's just say if H is equal to 0, then S1 equals S1 and S2 equals S2, so just don't move, else do this. Or we could have said, if H is not equal to 0 and then not put the else, but this just shows you kind of one way to use an if statement. So let's run our code by clicking the run, and it looks like I have an error there. Oh, I forgot a parentheses here. And let's run it again. And index exceeds, oh man, I really messed up that line of code. I'm sorry, this should be dx of 1 squared plus dy of 1 squared. Let's try that. And it looks like we are chasing the wrong cat. So it's not that we're chasing the wrong cat. I see if I put this back on point 2, it looks like something's not quite going right. My cat's, this blue one is not going in the right direction, and that's because I have a typo here in my code. So one thing I noted was that it looks like dx or dy or how I'm changing my location of S is incorrect. So let's go back to the lines where I did that. I see here that I did dx divided by H, which I also wrote that incorrectly on my slides. So I've now made that mistake twice. Hopefully I do not make that mistake again. So that should be dy divided by H. Let's run. So this looks much better where that blue triangle is chasing our green square. That looks great. So we need to do a similar thing for our next two, but first let's look at those triangles for our next two. So here between V and S, the change in Y is going to be S2 minus V2. That way, if that is a positive number, like we see here, V is going to run in the positive direction, but if it's a negative number, then we'll run in the negative direction. Here I have S1 minus V1. So right now in this picture, that's going to be a negative number, so which is correct because we want V to go towards the left in the X direction. And H is going to be the square root of dx squared plus dy squared. And we'll change the location of V similar to how we change the location of S. So looking back at our code, right around here, I'm going to calculate the distances between, it was S and V. And remember, I want to calculate these distances before I have moved any of my cats. Otherwise, I'll end up with this kind of weird thing where one cat moves more or less than it should. So dx, let's put this in the second location, is S of 1 minus V of 1. And dx of dy of 2 is going to be our y distance, so S2 minus V2. And then h, our hypotenuse, is going to be the square root of dx of 2 squared plus dy of 2 squared. We're going to have a similar if statement here. And let's just comment our code here. So this part we're going to move S, this part we're going to move V, and this part we're moving F. So we should change these here to V. And this should be dx because this is now an array. Let's do dx of 1, and then here we have 2 because I saved my delta x in the second location here. So let's run our code, and we see our cats are now chasing each other. If we wanted this to go slower so that we might see it better, we could just change this number to 0.5 or maybe to 1 or 2 if you really wanted to kind of go slower. If we wanted to also see how our cats are moving in time, which is not what the problem asked us to do, but if we wanted to see kind of how they've progressed over time, we could put a hold on here. Just make sure to remove before turning in. And this might help us debug our code. Like previously I had the bug. So let's click run, and we can see how those locations are changing. It actually turns out to be a pretty cool plot there. Okay, so that's our cats in corners problem. This problem was a final exam problem a couple years ago, but it was the same year that I gave the zombie exam, or sorry, the zombie lab as a required lab. So in that lab, students learned how to use the pause and how to plot like this. So if I wanted you to pause, I would on the exam, I would include some videos to kind of help you do that because we haven't covered that in depth. So I hope this is helpful, and I hope you enjoyed the Cats in Corners problem.